There's a theorem called the squeeze theorem. It's also called the sandwich theorem. And this theorem helps us when we have to find the limit of something that doesn't seem easy enough to find on its own, or we're not able to plug things in and get the right answer. So this is the main basis of the squeeze theorem. If you have a function f of x and another function g of x and then another function h of x, and g is between f and h and equal to, then we can say that the limit as x approaches a of f of x is equal to the limit as x approaches a of h of x, and that's some value, so we call that L for now. So therefore, since f of x and h of x have the same limit, it means that the limit as x approaches a of g of x will also be the same as the others, since it's sandwiched in between or squeezed in between the other two. So here's just a visual of what this means. So you have f, which is your blue function. You have h, which is your green function. So if I wanted to find g, g is sandwiched in between f and h. And you can see at this point a, they all have the same limit, in this case L. So we use the theorem when we come to some tricky things like this one. So when I look at this example, I have the limit as x approaches 0 of x squared sine of 1 over x. So if I try to break it up, let's say by doing the limit as x approaches 0 of x squared times the limit as x approaches 0 of sine of 1 over x. So if I try to break it up this way, I can't actually break it up this way. If I plug in 0, right, this one I know is going to equal 0, but when I plug in 0 here, I get 1 over 0, which is undefined. However, the sine function, if you think about what the sine function looks like, it's an oscillating function, right? It's one of those functions that goes like this. So since it's oscillating, we know that this part does not exist. So we can't use the actual, like, breaking it up and say 0 times does not exist is does not exist. But what we can do is we can think about the sine function, right? So if I have a sine function, we know that the sine lies between 1 and -1 when you have it on the graph. So between 1 and -1. That's where it's like capped off for the range. The y values won't go past 1 and -1. So we have this function here, and what we're going to do is we're going to make it just about the sine function right now. So we're just going to focus on the sine. So we're going to say, well, we know sine is between 1 and -1. So let's make an inequality and say that -1 is less than or equal to the sine of 1 over x, which is less than or equal to +1. So here we made an inequality, and that's what we're doing with the squeeze theorem or sandwich theorem, is we're trying to make an inequality. So it's between -1 and 1. Now what's missing, this is not exactly what we have, right? We have the sine of 1 over x here, but we also need the x squared. So I'm going to take this inequality and I'm going to multiply every piece of it by x squared. So I'm going to multiply this by x squared. I'm going to multiply this by x squared. And I'm going to multiply this by x squared. So just like whenever we do anything in math, you can't just do something to one side. So if I do something to the middle, I have to do it to both sides as well. So now I have -x squared is less than or equal to x squared sine of 1 over x, which is less than or equal to x squared. So now, based off of the squeeze theorem, I know that if I take the limit of the first function and the limit of the last function and find what the limit is and it's the same, that the middle will also be the same. So let's do that. So let's do the limit as x approaches 0 of -x squared. So if I plug in 0 here, this is going to give me 0. I'm going to do the same thing with the other side. So the limit as x approaches 0 of +x squared. And again, I'm going to plug in 0 and I get 0. So based off of the fact that they both equal 0, I'm going to say, therefore, the limit as x approaches 0 of x squared sine of 1 over x is equal to 0. So the limit would be 0 since the first function was 0 and the last function was 0. So the one sandwiched in between must also be 0. And here's what the graph of this looks like. So here's your x squared function, here's your negative x squared function, and this is our sine 1 over x function, this red one. And we can see that at this point of 0 here, right, they all are going to have a y value of 0. Okay, so let's look at another one. So typically the squeeze theorem is used when you have an oscillating function because you can't take the limit of an oscillating function since it doesn't exist. So here we have another limit as x approaches 0, and here we have two pieces. We have the radical piece, and then we have the sine of pi over x. So we want to prove that this whole thing equals 0. So again, we can't break it up, but we know that the sine of pi over x is going to be oscillating. So since it's oscillating, we know that it's going to be between -1 and 1 again. So we're going to set up the same type of inequality. So we're going to say it's between -1 and 1, so -1 less than or equal to, and we're going to do sine of pi over x, which is less than or equal to +1. Okay, we're missing this radical part, so I'm going to multiply everything by that radical. So square root of x cubed plus x squared, just pretend that that's in line. I'm going to multiply it over here too, x cubed plus x squared, and over here, square root of x cubed plus x squared. So I'm going to multiply this, and this gives me negative square root of x cubed plus x squared is less than or equal to the square root of x cubed plus x squared sine of pi over x, which is less than or equal to the square root of x cubed plus x squared. So again, we have that function in the middle, which is what we want, and then we're going to take the limit of each function. So I'm going to take the limit as x approaches 0 of the leftmost function. So that's going to be negative square root of x cubed plus x squared. Okay, I'm going to plug in 0 into here, and that gives me 0. So I'm going to do the same thing on the other side. So the limit as x approaches 0 of the positive square root of x cubed plus x squared. Again, I'm just going to substitute in 0. That gives me 0. Since they both are equal to 0, that means that the function in the middle must also be 0. So we'll say, therefore, the limit as x approaches 0 of the square root of x cubed plus x squared sine of pi over x is equal to 0. So we wanted to prove that, and now we did. Now this example is a little bit different because we don't have a sine function that's oscillating. We don't have to create the inequality ourselves. We're given the inequality, and we're trying to figure out information about the g of x function, which is just some generic function. So we want to find the limit as x approaches 1 of g of x. Well, we know what the end point functions are. So we're going to take the limit of each of those. So let's take the limit as x approaches 1 of the left end first, so of 2x. Okay, we're going to plug in 1 for x, and we get 2. Okay, we're going to do the same thing for the other side. So the limit as x approaches 1 of x to the 4th minus x squared plus 2. And we plug 1 in, and we get 1 minus 1 plus 2, which we get 2. So since they both are equal to 2, which when you're doing the squeeze theorem, both of the ends should be the same limit. They equal 2. Therefore, let's put a little therefore. Oops, I need to put the limit first. Then therefore the limit as x approaches 1 of g of x is equal to 2.